Some environments seem impossible to build on. Oceans shift, rivers rise, ice moves, but engineers have learned to listen, adapt and construct in partnership with the planet. In this video, we'll explore 3 remarkable examples of engineering marvels that battle nature's tough environments. From deep beneath the sea to shifting ice and rising tides, these projects show how vision and resilience can turn extreme environments into places of possibility. Imagine a tunnel so long it stretches further than the English Channel, and so deep it dives beneath one of Japan's most treacherous straits. The Seikan Tunnel connects Honshu and Hokkaido, Japan's 2 largest islands, by running beneath the Tsugaru Strait, a notoriously stormy and dangerous body of water. At nearly 54 kilometres long, with over 23 kilometres of that running under the seabed, the Seikan Tunnel holds the title of the world's longest undersea tunnel. But how did they build it? Construction began in 1971 and took 24 years of effort to complete. More than 3,000 workers faced unpredictable rock formations, high water pressure and the constant threat of flooding. And because Japan sits on a seismic hotspot, the tunnel had to be built to withstand earthquakes too. The conditions meant that sadly there were 34 fatalities during construction. Engineers used pilot tunnels, also called drift shafts, to assess geological conditions before full-scale excavation. Inclined shafts were also constructed for geological surveys and to transport materials and workers, and specialised drilling and blasting methods helped to detect water-bearing areas. Building the Seikan Tunnel meant solving problems no one had tackled at that scale before. It pushed engineering methods forward and set a new standard for undersea construction, quietly shaping how we think about infrastructure beneath the surface. After the catastrophic North Sea flood of 1953, which claimed over 1,800 lives and inundated thousands of square kilometres of land, the Netherlands faced a stark reality. Its low-lying geography made it dangerously vulnerable to the sea. In response, the government launched the Delta Works, a sweeping infrastructure project designed to protect the southwestern Delta region from future flooding. But how did they build it? The core idea was to shorten the coastline, reducing the number of barriers that needed reinforcement. This was achieved by constructing a series of dams, sluices, locks, levees, and storm surge barriers across estuaries and sea inlets. These were smart adaptive systems designed to respond to changing sea conditions. One of the most iconic structures is the Oosterschelde Kering, a 9-kilometre long storm surge barrier that can open and close depending on sea conditions. It was originally planned as a permanent dam, but environmental concerns led engineers to redesign it as a movable barrier, preserving tidal flow while still offering protection. Another standout is the Maaslandkering, near Rotterdam. Each of its 2 gates is the size of the Eiffel Tower laid flat. The barrier is fully automated and only closes during extreme storm surges, protecting one of Europe's busiest ports. Construction also required custom-built caissons, massive concrete structures floated into position and sunk to form barriers. Rather than reacting to past disasters, the Delta Works were designed to withstand future threats, including rising sea levels and climate change. The entire system is monitored and maintained with cutting-edge technology, and its principles have influenced flood defence strategies worldwide. Antarctica is like a continent-sized deep freezer, with winter temperatures plunging below -60 degrees Celsius and winds that can exceed 100 miles per hour. It's a place of total darkness for months on end, where the ice is a shifting, cracking shelf that can break off and drift into the sea. And yet, in this hostile environment, engineers have built something extraordinary. Halley VI, the world's first fully relocatable research station. Since 1956, Britain has maintained a presence on the Brunt ice shelf, but 5 previous Halley stations were either buried by snow or abandoned when the ice beneath became too unstable. So, the plan was hatched to design a fully modular research station mounted on hydraulic legs with retractable skis that could be relocated when needed. But how did they build it? Construction was a logistical challenge. All modules were prefabricated off-site, primarily in South Africa to ensure precision and reduce time spent building in harsh Antarctic conditions. Components, including steel frames, mechanical systems and insulated panels, were shipped to Antarctica during the brief summer window, when sea ice allowed access to the Brunt ice shelf. Once delivered, modules were towed across the ice using specialised vehicles. Each weighed around 9.5 tonnes and had to be carefully manoeuvred over unstable terrain. Construction crews faced -50°C temperatures, high winds and snow accumulation of 1 metre per year. All work had to comply with strict Antarctic Treaty environmental protocols, and with the Brunt ice shelf moving 400 metres per year, precise GPS tracking and ice radar was needed to monitor stability throughout the build. The station was completed in 2012 after 4 years of seasonal work at a cost of £25.6 million. This impressive series of structures was engineered to adapt, survive and evolve in some of the harshest conditions on the planet. From tunnels beneath oceans to structures that move with ice, these projects are just a glimpse of what engineering can achieve. At NES Fircroft, we work with some of the biggest, most exciting projects across the globe. Head to nesfircroft.com to connect with our teams and unlock the future of your engineering career. For more engineering content and career advice, subscribe to our channel, like this video and follow us on LinkedIn at NES Fircroft. Thanks so much for watching and we'll see you next time.